Welcome to the Chapter 12 review. Hopefully you'll understand what's going on after this video ends, but let's just get right into it. So for number 1, which of the following resonance structures is not significant contributor to the hybrid of the carbonyl group? Again, a carbonyl is just a carbon that is doubly attached or double bonded to an oxygen. Okay, and then you can have like an R group right here and another R group right there. That would be a carbonyl. So right here, what happened here is that this bond broke off for number 2, and it brought some negativity to the oxygen. So really, the oxygen gained some electrons, meaning that it became negative. It doesn't make sense that the bond would break towards a carbon, right? Because between oxygen and carbon, oxygen is more electronegative, if you remember from Gen Chem. Therefore, the electron should have been here and not here. That doesn't make any sense. You don't really see negative carbons by itself unless it's working with a Grignard, but you're not working with a Grignard. And so a negative carbon doesn't make any sense, okay? This is bad, right? So number 2 would actually be the correct answer because we are looking for something that is not a significant contributor. So number 1 is not the correct answer because you can actually find this. In fact, this is what a carbonyl is, right? Remember, it's a R group with a carbon. Then you have your electrons right there. So literally that is a carbonyl. So number 1 is wrong because it does exist. And number 3 is wrong because this also exists. So really you would have this right here. What is a alkanoid? Alkanoxide, sorry. So you would have 3 pairs of electrons, which is true for number 3. So 3 and 1 are incorrect. Number 2 would be correct, okay, because it's false, okay? So make sure you actually have not underlined, okay? Which is the following transformation would be considered a what? Okay, so if you see your answer choices have reduction, oxidation, etc., well, you can kind of focus on a carbon that has the reaction going on. Okay, so I'm not going to be focusing on these carbons, right? I'm actually going to be focusing on this carbon. Okay, so let's see. This carbon right here has 2 hydrogens, and this carbon right here, after the reaction took place, has how many hydrogens? Well, let's see. It has 3 bonds and another bond to hydrogen. So it has 4 bonds, one of them being a hydrogen. So it only has 1 hydrogen. So overall, we actually lost a hydrogen. So what is that? Well, technically that's considered an oxidation. So B would be correct. Therefore, lose H. You are oxidized, right? Oxidized. I'll just put oxy, okay? Because I don't know how to spell right now. It's like 6:52 in the morning. Pretty cool. If you gain hydrogen, well then you're reduced, okay? You're reduced. So lose hydrogen, you were oxidized, and if you gain hydrogen, you were reduced, okay? Because sometimes you're not working with just oxygen. Sometimes you're not working with just simple things, right? For instance, in the next problem, you might have no oxygens, right? So over here, list the following compounds in order of increasing. So we want oxidation to increase, and therefore I want to lose hydrogens, okay? I want to lose hydrogens. So lose hydrogens. And we want to go in the increasing order. So my first one should be the least oxidized. So let's look at this carbon. This carbon has 2 hydrogens. Let's look at this other carbon. Well, that carbon doesn't have any oxygen or hydrogens. It actually has an oxygen right there. So that looks like it would be the highest one. And over here, number 3, how many hydrogens does this carbon have? Well, let's see, 1, 2, 3 bonds. So one of the invisible bonds is a hydrogen. Okay, So I know for sure 1 is going to be the first one. But now, is the second one going to be the second or the third one? Which one am I going to pick? Well, whenever you're doing trends, right? You have your periodic table, something like this. And as you go this way, you will become oxidized. Yeah, that seems right. Oxidized, like the spelling. And as you go this way, you become reduced. Okay? So, you become reduced. So that's kind of like the general trend. For instance, you have, let's see, CNO, F. So therefore, what would happen if we compare nitrogen and oxygen? Are you going to say nitrogen is more oxidized than oxygen? No, you're not going to say that. In fact, you're going to say that nitrogen is more reduced than oxygen. Carbon is more reduced than nitrogen. Fluorine is more oxidized than oxygen. It's a general trend. If I had lithium, which you'll see in the next problem, you can say that nitrogen is more oxidized than lithium. So that's kind of like what you need to know, what you need to remember. So between 2 and 3, I'm comparing oxygen and nitrogen. So which one is going to be more oxidized? Oxygen is going to be more oxidized than nitrogen. So we're going to put nitrogen in the middle. So 1, 3, and we're going to say 2. Let's do that in a different color. We're going to say that 2 is going to be the most oxidized. Another way you can think of it is how many bonds are connected to oxygen. If you have 1 bond to oxygen, for instance over here, and then somehow you got 2 bonds to oxygen after a reaction, well, you became more oxidized. For number 4, the following transformation would be considered a what? So we have bromine, something happened to it and it just became a lithium. Well, bromine is somewhere over here. And again, lithium is on the left side. So technically you can say that bromine is more oxidized than lithium. But in this question, we went from bromine to lithium. So we went from a higher state to a lower state. Would you say that we were reduced? I would say that we were reduced. I would say that. So therefore, A would be the correct answer. And hey, you know what? I'm going to draw a smiley face as per tradition. Right there. He's very happy. Very happy person. Hopefully this is starting to make sense to you. Number 5. Which of the following reagents listed below would efficiently accomplish the transformation of this mess into another mess? Which is pretty bad. But let's actually do this. Let's actually write it out. So we have CH2, CH2, carbon that's double bonded. So CH2, CH2, carbon that's double bonded to this carbon. Okay. And CH2, 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 alcohol. And then we transform it into another thing. So CH3, CH2, carbon that's double bonded to another carbon. CH2, CH2. And then we have this. Okay. Cool, so an aldehyde. How did I know to put a double bond? Well, if I look over here, there's a CH2, which is like usually a peak, and then a carbon. So this carbon is attached to 1 carbon, 1 hydrogen, and 1 oxygen. So it only has 3 bonds, but carbon wants 4 bonds. The only way that I can make 4 bonds is if I double bond it to an oxygen. And it's pretty typical in this chapter, you know, ketones, aldehydes, carboxylic acids, they all have double bonded oxygens or carbonyls. So I said, well, most likely we're dealing with an aldehyde. So this is an aldehyde. Remember, it's like usually an R, carbon, and then hydrogen, double bonded like this, right? Or it can even be like this. Kind of like the general structure for aldehydes. So basically, I don't really care what goes on the left side. I don't care what goes on the left side. I didn't touch any double bonds, I didn't touch any carbons, etc. I only care about what happened to this alcohol. Well, this alcohol right here is actually considered a what? It's considered a primary alcohol. So it's a primary alcohol. And something happened to it and it became an aldehyde. Well, if you look at your answer choices, you have some reagents. You have potassium permanganate, you have this thing, and as a side note, this is actually the Jones reagent, which is basically hydrochromic acid, okay? So H2Cr O4. Okay, so if you see that on the exam, cross it out and replace it with H2Cr O4. Okay, very strong acid. You also have PCC, bromide, and 2 of these choices. Well, here's what we do. I'm actually going to erase some space and we're going to work this out. Okay, so the main reagents that you want to work with when you're dealing with alcohols and you form a carbonyl is PCC and hydrochromic acid. So for instance, if you want OH into kind of like this guy, just like a general carbonyl, you're going to be working with PCC or hydrochromic acid. Okay, so you can do that. But the difference is that for PCC, if you have a primary alcohol, you're actually going to convert it into an aldehyde. So I kind of gave you the answer already, which is C. But for hydrochromic acid, you have a lot of options. See, for hydrochromic acid, if you have a primary alcohol, you actually turn it into a carboxylic acid. So you turn it into carboxylic acid. If you have a secondary alcohol, you turn that into a ketone. Right? Okay. And if you actually have an aldehyde, if you turn that into a carboxylic acid, so carbox acid. But what if I have a carboxylic acid? So if we're going to turn that into an alcohol, usually a primary alcohol. So, well, not usually, but you're just going to transform that carboxylic acid into an alcohol, sorry. So, OH. And then for both of them, tertiary is no reaction. Okay, so that was it. That's basically it. That's all you really have to know. So for this question, we're working with a primary alcohol. If you treat it with PCC, it'll become an aldehyde. Very cool. So it's answer choice C. Now we have to find which product is formed whenever we treat this compound with lithium aluminum hydride and do an acid workup, which is just when you add an acid afterwards. So what I like to think of is that when I see lithium aluminum hydride, I kind of ignore it and I just replace it with hydrogen anion, okay? So basically it's a negative hydrogen because that's really all you're working with. So what happens here? Oh, and you should know the trend that lithium aluminum hydride is able to work with esters. After this problem is done, I'll make a chart for you right here and you can copy it down. So what happens here is that this bond, one of the bonds from the carbonyl, breaks off and makes a negative oxygen. Since this negative oxygen formed, there has to be a positive something, right? Because if you have a negative, well, where's a positive? So they could cancel out. Where is it? Well, the positive is going to be on the carbon right here, okay? So that carbon is going to be positive, and since he's positive, these electrons are going to go and connect with the positive carbon. Hence, we're going to have this structure right here, and it's going to take me about a couple of years to draw, but hopefully you'll still be in grad school or something. So let's do that. So we have an alkoxide, and then we have our added hydrogen. We have an added hydrogen. So that was good. But now one of the bonds can reform. So one of the lone pairs from the oxygen can actually come in and swoop back, right? They can actually come back. So if we do this temporary bond, carbon is going to have how many bonds? This carbon. Well, let's count. It's going to have 1, 2, 3, 4, 5 bonds. And that's not really good. You'd never want to see a carbon with 5 bonds. That's not good. So now it can either break this bond or it could break that bond. Which one am I going to break? I'm actually going to break the oxygen bond. So this bond can actually break out towards the oxygen, making this one negative. Since we have something that's negative, something else has to be positive. And what's positive is this carbon right here. So again, we're going to have another positive carbon. Okay, so let me make that plus sign a little bit bigger. Now another hydrogen anion could come in, and it's like, ooh, it's free real estate, you know? And it can actually come in to the carbon. Now what happens here is that, let's get a color. What happens here is that we have an alkoxide formed, chain that way, this way, and let's do this. So now we have 2 hydrogens that have been added. Okay, so let's do hydrogen and another hydrogen. Okay, and also don't forget that we formed a double bond as well. We formed a double bond. So really, the oxygen shouldn't be negative. My mistake. Okay. There we go. Of course, this reaction and many other reactions are located in the chapter 12 general lesson video. So if you don't want to see this reaction, you could skip ahead. Okay. So after that happens, this bond can just go out here back into the oxygen. Back into the oxygen. So what we have now is this guy. I'm kind of exaggerating it. Okay. So you can really see the hydrogens, and I have enough space to work with. Okay. So technically you should be done with that, and after this step 1 is done, we're going to treat it with some hydronium, which is just an acid workup. And what you should know is that in acid workup, your hydroniums, there's like millions of them, they are attacked by the oxygen. So they're like this. One of these bonds break, releasing a proton or just a positive hydrogen, and the oxygens are going to pick up that hydrogen. It's going to pick up this hydrogen as well. Right. Of course, there's many hydroniums. I'm just lazy. I don't want to draw another hydronium. So just pretend that there's like 2 hydroniums and you're reacting with it. So therefore, you would now have some alcohols over there. Okay. So you now have 2 alcohols that are connected by 1, 2, 3, 4 carbons. Well, look, over here you have 1, 2, 3, 4 carbons. And so what is your answer choice? Your answer choice is B. For A, you still have a cyclic compound. For C, you have a cyclic compound. For D, you actually have an aldehyde, which is not good. And for E, you have an ester, which is not good either. It should be B. And now we do our chart that you need to know for the exam. Now, in the case of lithium aluminum hydride, it can actually convert carboxylic acids, can convert carboxylic acids, carbox acids, and it can do ketones, aldehydes, and esters. So basically it can do almost everything if it has a double bond. So it can convert carboxylic acids into primary alcohols, it can make ketones into alcohols, etc. Right? If you do an acid workup afterwards. However, if you're working with sodium borohydride, cannot work on esters or carboxylic acids. But it can work on ketones and aldehydes. Okay, so lithium aluminum hydride can convert carboxylic acids, ketones, aldehydes, and esters into alcohols. However, sodium borohydride, it can work on ketones and it can work on aldehydes, but it will fail on esters and it will fail on carboxylic acids. Okay, so for number 7, which of these compounds cannot be reduced by sodium borohydride, which is this guy. So which one cannot work? Well, over here on this center carbon right there, that is an aldehyde. And we do know that for sodium borohydride, an aldehyde can be converted into an alcohol. So this is not correct because it can happen. Over here, you just have a ketone. Sodium borohydride can take out a ketone, which is not correct. Right here, we have what? On this carbon, we have COOH, which is a carboxylic acid. And you know from this chart or from these paragraphs, sodium borohydride cannot work on carboxylic acids. So this one would be the correct answer. Okay. And over here, what else would happen? Well, for sodium borohydride, you can't work with esters as well. See, that wouldn't work. So technically, A, B, C and D would actually be correct. So if there was a multiple choice question that said 2 of these compounds, well, you would pick that. Okay, so 2 of these compounds cannot be reduced by sodium borohydride, that being the carboxylic acid and the other being an ester group. Okay, which of these compounds will not be reduced by lithium aluminum hydride? Okay, well, the only thing that won't be reduced by lithium aluminum hydride is something that doesn't have an oxygen. So remember that over here, this is an aldehyde, which is pretty good. So this is wrong. This is an carboxylic acid, which is also good. It'll make that into an alcohol. So that's wrong too. Over here, we have an ester group, and lithium aluminum hydride can really work on ester groups. They're pretty good. Over here for A, this wouldn't work. Why would it not work? It wouldn't work because there isn't any oxygens to work with. There's no carbonyls. It's just an alkene. And we don't really use lithium aluminum hydride or sodium borohydride for basic alkenes. Okay, so this compound would not be reduced by lithium aluminum hydride. Number 9, which of the reagents would effectively accomplish the transformation of 3-methyl-3-cyclopentanone into 3-methyl-3-cyclopentanol? Well, luckily they gave us the compounds because I wasn't going to write it out. That's terrible. But basically, none of this changed. Okay, like the bottom half didn't change, okay? The only thing that we changed was this, okay? So we went from this guy into this guy. So we basically converted a ketone into an alcohol. So how do I do that? Now, do I use H2 and palladium? Well, that doesn't make any sense. Why would I use hydride and palladium? That's actually going to remove an alkene. So it actually would remove this alkene, or I should say this alkene, right? So that doesn't make any sense. C is wrong. If I use lithium aluminum hydride and then do an acid workup, this double bond is going to disappear, making it an alkoxide, and then an acid workup is going to create an alcohol. which would be correct. Okay. What about B? Sodium borohydride and then an acid workup. Well, sodium borohydride, it can actually take out a ketone and replace it with an alcohol. So that would make sense too. We have two correct answer choices, but answer choice D would be correct because it says more than one of these choices. So lithium aluminum hydride and sodium borohydride can actually take out this alkene, or this carbonyl, and replace it with an alcohol. For number 10, how do we make this product from that reactant? Okay, so how do we make that? Well, let's go over here. Nothing changed except we made a secondary alcohol into a ketone. Okay, so I basically cut off anything that wasn't reacting, and that's the bottom half. How do I make a secondary alcohol into a ketone? Am I going to use H2 with platinum? Well, no, because the platinum is actually going to react with the alkene, and you wouldn't have this double bond. Okay, it wouldn't touch the alcohol, so that would be incorrect. Okay, so we can already say that C is wrong. And do you see any bromines on our product? I don't see any bromines on our product, so Br2 would be wrong as well. Now it's either A or B. It could be E. Well, potassium permanganate, in this context, in this chapter, potassium permanganate, would actually make a carboxylic acid into what? Would make that into an aldehyde. Okay. Or rather, I'm sorry, I was thinking about something else. It actually makes primary alcohols into carboxylic acids. I don't know why I said that. My mistake. So it would actually make primary alcohols into aldehydes, or carboxylic acids, sorry. It's really early in the morning. My apologies. So first of all, we don't even have a primary alcohol. We actually have a secondary alcohol. So potassium permanganate isn't a good option, okay? Because you would need a primary alcohol to make it into a carboxylic acid. And secondly, we don't even have a carboxylic acid. So A is wrong as well. Therefore, E is wrong. And B would have to be correct. Now, remember what I said about Cr, or I should say CrO3 with this? Well, technically, it just becomes hydrochromic acid. Okay? That's just hydrochromic acid. And hydrochromic acids, they make secondary alcohols into ketones. So you would actually use the Jones reagent. This is called a Jones reagent. Okay, so the answer would be B. Okay, remember that potassium permanganate makes primary alcohols into carboxylic acids. For question 11, which product is formed whenever you do the following reaction? Now we're reacting with some Grignard reagents. So we have CH3 with the Grignard. So it's like this, MgBr. What I like to do is that I like to ignore the MgBr. Okay, so I typically erase it, or I scratch it out on a test. And I just keep the one carbon. Okay, so let's say it's like right there, and let's erase that. And let's just say we have a CH3 negative, okay? Let's say it's negative. Okay, since that is negative, what's it gonna do? I'm actually gonna draw it out really quickly, so just wait a second. Well, what happens here is that for the bond to break, this one would take out the electrons, forming a negative alkoxide. Okay, since that is negative, this carbon right here has to be positive, right? And these electrons are going to be really attracted to him. he's going to break out. Well, we have enough to do this a lot of times. We have enough, or I should say we have excess amount of Grignard reagents. So now we have a methyl group over here, okay? And then again, these bonds can actually come back and reform the double bond, okay? It could reform the double bond, and I should just draw it out right here. Okay, so technically we still have the double bond, and we're going to have an attached methyl group as well. But now this carbon has too many bonds. It has 5 bonds. Therefore, it's going to break out right here and basically form an alkoxide, making another positive carbocation. And another one, another CH negative, CH3 negative is going to come in, and he's going to join right there. Okay? He's going to join. And then one of these bonds is going to break off to form another alkoxide. Okay? So here we go. We're going to draw this out. So we have an alkoxide right here. And another one. And then we have 2 methyl groups that are over here. So whenever you're working with esters and Grignards or anything like that, specifically for esters, you will be doing a double addition, quote unquote double addition, meaning that whatever you're reacting with, in this case CH3, is going to add twice under the carbonyl. Okay, so notice that my carbonyl now has 2 methyl groups. Afterwards, we're going to react it with some acid, and the acid just makes these alkoxides into alcohols. Okay, so that's called an acid workup. Okay, acid workup. And so we remove the alkoxides and just add a proton to them, making some alcohols. Okay, so therefore this alcohol became a tertiary alcohol. Okay, we now have a tertiary alcohol. So A is wrong because somehow you still have the ring. That's bad. There's still a ring in B. That's bad. D, you have an aldehyde, which is not good. Okay, so it has to be C. Let's double check. So one of my alcohols is tertiary. Okay, so that's pretty good. And the other alcohol is primary. And this alcohol is primary. So that makes sense. We don't have a ring, and we also have a tertiary alcohol, which is exceptional. Perfect. So the answer is C. For number 12, we have to make this compound through a synthesis reaction using Grignard reagents. Okay, so it's actually not that bad. And here's how I do it. Okay, so notice that we have an alcohol, and it's on the hexane, cyclohexane. Okay, well, if we have an alcohol or whatever we have on the cyclohexane, well, most likely I want to have a ketone. Okay, or basically a carbonyl. Okay, so the logic behind this is the Grignard reagent is going to take out the double bond from the carbonyl, and then we can do an acid workup to create an alcohol. But in order for us to have this compound, I want the carbonyl to be on the cyclohexane. So A is wrong because it's on the cyclopentane, so that's wrong. B looks okay, and C looks okay too. D is wrong because, again, there is a carbonyl on the cyclopentane. So it's either B, C, or D, or E. Okay. So what happens here? Let's try C. Well, if I add magnesium, so in my first step, if I add magnesium, well, then I could just get magnesium bromine on this cyclohexane. And actually, this is wrong. Why is it wrong? Well, how am I going to get my cyclopentane? Where is that? I have 2 cyclohexanes. That doesn't make any sense to me. So that's wrong too. Okay. Well, now it has to be B, or it could be E. Let's check it out. For my first step, I could treat the bromocyclopentane with magnesium to make a Grignard. So I could just have MgBr, and then afterwards I can ignore it and just make a negative cyclopentane. Okay, that's what I'm doing. So this carbon right here is negative. So now this bond is going to break out towards the oxygen, making a positive carbon, and this negative carbon is going to be attached to the positive carbon. Okay, so this is what we have now. We now have a cyclohexane with an alkoxide. And then we also have a cyclopentane. It's pretty ugly, but it's alright. Now, if we actually make an acid workup, we just convert the alkoxide into an alcohol. So basically, the alkoxide is removed, and we just add a proton or a hydrogen to the oxygen, making an alcohol. And this is actually a tertiary alcohol, similar to the tertiary alcohol right there. Hopefully you guys like this new ink color. I think it looks pretty good. It's like a pinkish purple, I guess. Not sure. So there we go. That was the logic behind it. So again, to recap, because we have an alcohol on the cyclopentane or cyclohexane, you want a carbonyl over there. It could be a ketone, aldehyde, or whatever. You just want a carbonyl. So therefore, B and C looked pretty good because this cyclohexane had a carbonyl. C was wrong because you had two cyclohexanes. Where am I going to get my cyclopentane? And then B, we just went through the steps. It was pretty self-explanatory. How could the following synthesis be accomplished? Okay, so we made this secondary alcohol, and we treated it with something, and it made this product. Okay, well, do you see any chlorines, right? Do you see any of that? Not really. So A and B are kind of iffy because Sokol, which is what I call it, they actually just add a chlorine. So they kick out this this alcohol and make a chlorine. Okay, so we have this now. But if we add magnesium, that wouldn't make any sense, right? You don't really see magnesium chloride. You see magnesium boride, and you don't see lithium chloride either. It's pretty weird. So that wouldn't bode well for me, okay? That wouldn't make any sense. So A and B are wrong, simply because you don't really mix magnesium with chlorine, at least not in this class. Same thing with lithium. So A and B are wrong. But what about PBr3? Okay, well, PBr3, that's just going to replace the alcohol with a bromine. So we have alcohol with a bromine. Replace that. And then we're going to treat it with magnesium. So if we treat it with magnesium, we have MgBr. And MgBr, we can actually ignore it and the bond with it and just say that this carbon right here is now negative, okay? Now, notice that for C, this was done in an ether. Okay, so an ether means that it's going to facilitate this Grignard process. This is why we do Grignard reagents in ethers, is because if you did it in an acidic solution, it's actually going to rip off a hydrogen and do a completely different reaction, which is not what you're trying to go for. Okay, so make sure that you're doing your labs and your tests in ethers. Okay, so that's that. We now have an ethylene epoxide. It's like that. Okay, so CH2, CH2, and then oxygen. Now this is going to be acting as what? It's going to be acting as a base. It's going to be acting as a base. Now, for this one, this compound is symmetrical. Symmetrical as in this has the same amount of hydrogens as this guy, okay? So that's symmetrical. So it doesn't matter if I break this bond. It doesn't matter if I break that bond. Just pick your poison, okay? So we're going to break this bond, making this carbon into a positive and making this one into an alkoxide. Okay, so that made that into an alkoxide. Okay, now we have a cyclopentane. He's going to attack right here. And we just have two more carbons to add. So 1, 2, and then we're going to add an alkoxide. Okay, there we go. Now after that, we treat this with hydronium. So that makes the alkoxide into an alcohol. Okay, so now we made a primary alcohol. After we make a primary alcohol, we're going to treat it with PCC, right? So what happens when you add PCC to a primary alcohol? Well, the only thing that can happen for PCC on a primary alcohol is to make an aldehyde. So I'm not going to show you that reaction, but now the alcohol instead becomes an aldehyde, which is what you have. So that's CH2, carbon, there's a hydrogen, and then a double bonded oxygen. So that is an aldehyde. So C would actually be the correct answer choice, C. So for number 15, which of the following reactions, reduction reactions, would be unsuccessful? For A, we're treating something with lithium aluminum hydride. And I'm really focusing on the carbonyl and whatever is around it. I don't care about this chain. I don't really care about this chain either. I'm just caring about the ketone, or not the ketone, but the carbonyl and the adjacent carbons. So over here, what is this? Well, we have a carbonyl, another oxygen, and then a carbon. So that right there is an ether, or not an ether, an ester, I'm sorry. So that is an ester. So we have an ester, and we're reacting it with lithium aluminum hydride. So yes, lithium aluminum hydride can actually react with esters, okay? So this is wrong because that would be successful. We are looking for something that is unsuccessful. Okay. For B, we're reacting an aldehyde with sodium borohydride. And I know that sodium borohydride can actually react with aldehydes to give me an alcohol. Okay, so it can give me an alcohol. So this would actually be incorrect as well, because that would work. For C, we have a carboxylic acid, and then we're reacting with hydride and platinum with high pressure. Well, this doesn't make any sense, because this only works for alkenes. And if you forgot what an alkene is just a double bonded carbon. So it's like a carbon, double bond, carbon, and then yada yada, whatever, you know? So C wouldn't work. That would definitely not work, okay? And if you're confused on what this CH2 by 10 means, it just means that we have CH3, CH2, and then we have like 10 of these peaks, okay? So it's nothing special, all right? So that wouldn't work. So the answer would be C. So this would be the correct answer. Let me see if I can circle that. So C would be the correct answer. What about D? Let's just kind of, so you feel more comfortable, okay? Well, this is just a straight up ketone. And the reason why you have C6H5 is because it's like cyclic and there's another compound, but it's not important. So this is the ketone. And ketone with sodium borohydride, well, yeah, you can react a ketone with sodium borohydride, okay? So D would actually be incorrect because that would just give you a secondary alcohol. So D would be incorrect. So it'd be C. So what is the major product formed by the reaction of toluene with potassium permanganate? Well, I don't know how to draw toluene, and you probably don't know how to draw it either because it's not given to us. But context clues, the only thing that potassium permanganate does in this chapter is make a primary alcohol into what? What does it do? Well, it makes a primary alcohol into a carboxylic acid. Okay, so it makes a primary alcohol into a carboxylic acid. So most likely, if you don't know how to draw toluene like me, and you just want a lucky guess, most likely it's going to be the one with carboxylic acid, okay? So let's try to find our carboxylic acid. Okay, well, over here, we have a ketone, and then a lot of alkenes, and carboxylic acid right there. That looks okay. And that looks good too. But actually, this is an aldehyde right here. E is an aldehyde, so that's wrong. This looks all types are wrong. Like, why do we have 5 alcohols? That's terrible. This is just a primary alcohol. I don't know why you have too many double bonds right there. Okay, like, This just seems like a mess. So it's either between B or C. I feel a lot safer with B because I at least know there should be like a benzene ring somewhere. So I'm just going to go with B and say that it's a carboxylic acid with a benzene ring attached to it. Okay, so the answer would be an ugly B. It would be B. Good. Okay, for number 17, we're reacting some methyl magnesium iodide with this compound. So what would be the product? Okay, well, right here, ignore the magnesium iodide. So we have a negative methyl group, okay? But what you need to know is that for Grignard, which is just like MgBr, MgI, etc., or just lithium with some carbon chain, Grignard acts as a very strong base. Very strong base. Now it's so strong that it wants to actually rip off some hydrogens, okay? So it's so strong as a base that it wants to rip off any available hydrogens that it can get. So therefore, this hydrogen bond breaks, releasing a proton, and the methyl group is actually going to take out this hydrogen. So CH4 is going to be in the product. Therefore, 1 would be correct. You now have an alkoxide, so we have like this, okay, and then you have like your little benzene ring. I'm just kind of like cutting it off to, save time. So now you have an alkoxide, and then the MgI, which is positive, is going to be attached to this alkoxide. So you're going to have kind of like MgI. Okay, so this is why we don't do Grignard reagents whenever there's an alcohol or whenever there's a proton in the solvent, okay? Because that Grignard reagent is actually going to always attack the alcohol, and it's always going to attack the hydrogens. This is why we don't use alcohols or reactants that have alcohols on them, okay? Normally you want them to react with the carbonyl, but that wouldn't happen in this case because a Grignard reagent is a very strong base. So the bottom line is, if you have an alcohol and then you have a Grignard reagent, the Grignard is going to go for the alcohol instead of the carbonyl. What would be the product A of the following reaction sequence? Okay, so we have a secondary alcohol and PBr3. Now PBr3 works for primary and it works for secondary alcohols, and it just makes those alcohols into bromine. Okay, so now we have 1, 2, 3, 4. We now have a bromine right there, and then we're going to add some magnesium, so now we have MgBr. And as you know, we can just ignore the MgBr in the associated bond and just say that this carbon right here is negative. Okay, so that's negative, and afterwards you're going to attach some hydronium. Okay, now you're saying, well, what are you saying? Not hydronium, but water. So you're saying, Brian, there's no water, that's deuterium. See, I'm smart, I know what deuterium is, Brian. I'm like, okay, good for you. But basically deuterium is just heavy hydrogen, okay? So it's heavy hydrogen, and you can just kind of pretend that it's just water. So if you have it like this, one of these bonds is going to break, releasing a positive deuterium atom, and then this carbon is going to pick it up. And thus, we would have something similar to answer choice B. So we would have something like this. Okay, there we go. So answer choice B would actually be your correct answer choice. It's just deuterium. There's no ether formation, there's nothing like that, okay? So what about this one? We have CH3, CH2, 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 and then OD, which is like an alcohol. And what about E? CH3, CH2, 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 deuterium. That's not right either. It would have to be B. For 19, we have to react some product, or we have to react some reagent with lithium aluminum hydride. Okay, so first of all, I ignore this. I'm saying that it's an hydride, anion. This one breaks off towards the oxygen, making this a positive carbon. He's going to be attracted to the positive carbon right there. So now we have this guy, and an alkoxide right there, and then we have an added hydrogen. And let's actually do that added hydrogen in a different color, probably purple. Do that. Okay. So now after that happened, this bond can actually reform again. Well, it could reform. No, actually it wouldn't reform. Why? We only have one lithium aluminum hydride, and there are no ester groups. So it's just a simple H addition. But what happens here is that this H actually can go in from the bottom, or it could go in from the top. So there is some stereochemistry on this carbon now, okay? So likewise, I could have done this. I could have done something like this, hydrogen, and then a wedge methyl. Or I could have done a wedge hydrogen and then a hash methyl. So it doesn't really matter. The only thing that does matter is that this stayed the same, okay? So my answer choice should have the same configuration. That doesn't change, okay? So let's see. 1 looks okay. 2, this was changed. This was inverted. So that's wrong, okay? That's wrong. This is not right. This looks okay. What about 4? Well, that's wrong because that was inverted as well. Okay, that changed. That's wrong. Okay. Now for 1, we have the alcohol, which is formed by an acid workup of the alkoxide. And then we have a hash hydrogen. And on number 3, we have a wedge hydrogen. So for a split second, that hydrogen has 2 options. It could go in via the hash route, or it could go via the wedge route, because there is some stereochemistry, okay? So the products is kind of like an equal mixture of 1 and 3. So this is correct, and that is correct as well, okay? So there is some stereochemistry whenever you do sodium borohydride or lithium aluminum hydride. The hydrogen that you add, depending on the carbon, can actually choose the top route or the bottom route. It has an equal potential of doing both, okay? So for the last question, which of these will not produce a primary alcohol? Okay, so we have CH3 and some other stuff, whatever. Basically, I don't really care what goes on the left side. I just care about the right side, okay? So we have a CH2, a carbon, right? So we have a carbon, and then we have an H and O. So it's like this, okay? So that is technically an aldehyde. So yeah, let's just do that. That's an aldehyde. And then you're treating this aldehyde with lithium aluminum hydride, okay? So lithium aluminum hydride, the aldehyde is going to come off. We add hydrogen right there. So now, that's a very bad H, actually. So now what we have here is that we have some R groups, like who cares? And then we have an alkoxide and 2 hydrogens. Well, afterwards I could treat this with a hydronium, which is an acid workup, and convert my alkoxide into an alcohol. So the alkoxide can change from this primary alkoxide into a primary alcohol. Now notice that I don't care about the hydrogens, I'm really caring about the carbon chain, which I designated as R, okay? So that is a primary alcohol, which is incorrect because we want something that does not produce a primary alcohol. So this is wrong, okay? Now, for the second one, for B, we have some weird things, but basically it's like this. It's like CH3 carbon, that carbon has a CH3 and hydrogen, and then CH2, and then magnesium bromine, which basically means that we can get rid of that bond and make this carbon negative. Okay, so that carbon is negative, and then we have an ethylene epoxide. So this is acting as a strong base, but this has 2 hydrogens and this has 2 hydrogens as well. So it doesn't matter which one I break. Let's say I break this one right here. Okay, well that makes a positive carbocation. This attacks this guy. Thus we have this. So that was my original compound. We're going to add 2 more carbons. So let's see, 1, 2, and on the other one we have an alkoxide. Okay, so whenever you're reacting with R, Mg, Br compounds, or basically R chains with Grignard reagents, and you're reacting with ethylene epoxide, well, ethylene epoxide, you're just going to be adding 2 more hydrogens, or sorry, 2 more carbons to the Grignard reagent. Okay, so notice that I have 1, 2, 3, 4 carbons. After I react with the ethylene epoxide, I'm going to have 6 carbons. Let's make sure. 1, 2, 3, 4, 5, 6. And on the very last carbon, you're adding an alkoxide. After you do the acid workup, you're going to remove the alkoxide and form an alcohol. Okay, so it's just a double carbon addition. Simple. And what do you know? That is a primary alcohol, which is not good. Okay, so B is wrong as well. B is wrong. What about C? C is another Grignard reagent, except it uses, I'm sorry, I was looking at D. Well, I guess we'll do D first. So it's another Grignard reagent, but instead it uses lithium. So we have CH3, CH2, 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 and a lithium. But what do you know about lithium? Lithium is just ignored with the bond. Okay, and it makes that carbon negative. Make that carbon negative. And this is an aldehyde. So we have a carbon right here, alcohol, or not alcohol, but carbonyl, hydrogen, and a hydrogen. This breaks out. He attacks the positive carbocation. Let's go over here. So now we have carbon, alkoxide, hydrogen, hydrogen, and let's see. 1, 2, 3, 4, and then that right there. Afterwards, we treat it with acid workup. Acid workup. And what do we have now? Well, technically that is still a primary alcohol. So that is a primary alcohol. This is not what we want. We want something that does not produce a primary alcohol. Okay? Cool. So D is wrong. And over here, I'm not going to do this because you have a lot of carbons and whatever, but you're basically reacting a carboxylic acid with lithium aluminum hydride. And carboxylic acid, whenever you react it with lithium aluminum hydride, is going to give you a primary alcohol. Okay, so E would not be correct. But what about C? C, you have a cyclic compound. Let's ignore it. And let's just say that that you have a ketone, okay, or something like that. Well, I know for sure that, let's do it like this. Let's do R chain, carbon, and then CH3. Let's do an ketone, okay? So we have sodium borohydride, which is just, you can ignore it and just say that it's a H hydride anion. This breaks out, making a positive carbocation. This hydrogen is going to be attracted to the positive carbocation. Thus, we have this. We have a secondary alkoxide and an added hydrogen. Okay, and after that, we can just do an acid workup, and create an alcohol. But what's important that you should know is that this alcohol is secondary. So we have a carbon and we have another carbon. So this is actually a secondary carbon, or secondary alcohol, I should say. And therefore it doesn't produce a primary alcohol. So that is the correct answer. The correct answer is C. Simply because this ketone, quote unquote ketone, is reacting with sodium borohydride. It takes off a double bond, makes an alkoxide, a secondary alkoxide. and then we do an acid workup. So from the secondary alkoxide, we create a secondary alcohol. So that was it for the chapter 12 review. Hopefully now you understand the material a bit better, and if not, you can watch the previous videos, and I hope that you do amazing on your next exam. As always, I hope you have a great day. Thank you for watching, and I love you. Goodbye.